My name is Oleg. I work at Capish Nordic. We are a local company. We're actually sitting here at Store Target. And what we do, we develop solutions for knowledge management and analytics. And this will be a story of how we use Semantic Web technologies internally. Yes, so the agenda, just to explain a little bit what the plan for the evening is that well, first I will need to give you a little bit of a context just to understand how the need for Semantic Web technologies came naturally. I will need to present a little bit the technical side of what we do and why we have such affinity with Semantic Web. And then naturally tell a bit more about how exactly we use the stack. I will not be telling very much about what these things are. Probably many of you already know a bit. I will rather focus on exactly the features which attracted us. And then we may have take questions and discussion maybe. And then as announced, there will be a little dessert in the form of something completely different. Namely, we will look at a little bit at how one can push the limits of all as an ontology language and then apply it to solving a logic puzzle. As said, first about Capish, what we do. Well, as I said, we develop knowledge management solutions, and well, knowledge management means that, and of course we use computers, so we need to represent the knowledge somehow formally. So we need to have a data model, and our data model happens to be a graph with nodes and edges, which we call relations. And relations are directed and labeled, so they have names. And nodes, well, we call them objects, or also another more Capish-specific word, we call them columns. But I will skip that and call them objects just to avoid confusing you. So graph. So the relations are quite simple. And then let's look a little bit at the nodes itself, at how they are represented. And we use XML for that. And this is an XML of a well, typical Capish object. So what does it look like? It's well, it's one object. And it's represented with a single O tag, XML tag. Then it has several attributes in here. Well, I'm showing only three, the most important ones. There are more. Basically, object type, well, this is what it says. Concept is an additional explanation, one could say. And this is a so-called the Dewey Decimal Classification System code. It's a quite well, famous and popular library system, which is quite old. And one can be pretty sure that 50 years from now it will still be recognized because it has survived so many years by now. Then the object itself, it naturally has to have data, and the data come in form of fields which have name and the value, like here. Some of the fields, yes, the value may have an attribute, but these are details. Some of the fields may be sitting in a group which has a name. And then the relations, they also coded with the XML. So the relation has a name, then it says to which object type it points, and then the reverse relation also gets a name, and then there is a key of the object it's pointing at. The same holds for this object itself. Of course, it also has a key. It's a unique identifier. So, well, what we see here is actually there are a few levels of abstraction, one could say. There is the structure of the object itself. on one side, and then on the other side there is the content, the data. For example, this date, or this age, or this comment, or this value. So these are all data. And then in between, there are the names of the fields, and there is the name of an object, and this we call it concept, and itself the GUI code, which we call the main. They are somehow in between, so they are metadata to these data. And then, so what is a natural name for a metadata of a graph data model? Well, it's ontology. And so we have, so we call our metadata system ontology, and it has been called so from the beginning. If we simplify what it is, it basically, for us, it's, if you like, it's a schema which describes which object types there are, which properties they have, which fields, and then which relations exist between the objects, so that one object has a relation, and then the relation in its turn points at some other object, or maybe some other type. Well, this is a simplified view. In reality, it looks a little bit more like this, because well, one has a lot of technical details, and one has a grammar, and one wants to reuse the literals, and so it becomes a bit more complicated, but conceptually it is like that. And then, well, the important part, of course, of our activities is conversion of the data from the formats which are quite common to the format, to our format, to Capish XML. And this conversion naturally has to be done in accordance with our schema, with the ontology. We have developed a conversion system for that. It's called Capito, so that you just know what the slides say. And it's exactly the requirements of on this system that brought us to using Semantic Web technologies. What the system does, it actually, well, it does essentially two steps. The first step is, of course, well, when you have to convert some data, of course, they are never perfect. Of course, they need to be cleansed, harmonized, we call it, maybe reshaped. So plenty of operations that might be necessary. So this is the first step of data conversion. We call it harmonization accordingly. And then there is the second step is, if we simplify, you could say it's essentially renaming. Well, it's more complicated than that, but it's it. So first the data is shaped, and then it's renamed to conform to our schema, to our ontology. That's the second step, and we call it ontologizing. Purely internal names, but quite explanatory. Before we developed it, of course, we came up with some requirements, and there were quite many. Of course, we'll focus on some, on the most interesting ones for us. Well, of course, there is the very general and basic point that it has to take care of the routine operations and prevent user errors. And then we also wanted that it would be graphical, that the users don't have to program, not with the code at least. And then, of course, support the two previous steps, harmonization and ontologizing. Now comes the essential bits. When we formulate the conversion, we, of course, want to refer somehow to the schema that has to be that we have to conform to in the end. So we have to refer to the ontology, so we have to formulate the conversions in terms of the ontology. And then, of course, the ontology is also a moving target, so to say. It's being developed all the time. So the terminology gets improved, updated, aligned, and for one thing, and for the other thing, the structure of the ontology itself, when we were developing the conversion system, it also was subjected to quite a bit of change. Mostly it was upgrades, so more complexity, you could say, more features. If you yes, more features would be more correct. And finally, the maintenance of this ontology, or terminology if you like, it is a separate task. So you don't want necessarily to mix it with the conversion itself. It may be even different people who do it. For example, so here is how we could represent access to Capish Ontology by different interested parties. So one person could be, of course, the one doing the conversion, and then the person interacts with the Capito, which in its turn has to be able to read Capish Ontology and then formulate conversions and then do the work. But there may be another person which is not expert in conversions but expert in terminology. So you need a separate tool, a separate channel for interaction with Capish Ontology. That's another requirement. Well, from that, from these practical requirements, you could deduce requirements on the data layer which is going to be used. So what are we expecting from the data layer? Well, first a simple one, nice to have, so to say, that everyone wants to use something standard and free, so would be good. Then, of course, it must be expressive enough for modeling our ontology. It goes without saying almost, but at the same time it doesn't say it here. It has to also be expressive enough to model all the conversion steps, all the operations which we perform on our data. Then, as I said previously, it must survive changes in the schema, and it concerns both when the ontology itself, the content of it gets changed, or the structure of the ontology gets changed. Would be nice if it didn't break too much for us, those who develop the conversion system. And again, the capable of reconciling disparate data sets. What is meant here is that it's totally different concerns. One is the maintenance of the ontology, and another is the conversion of the data. And still, your data layer needs to somehow marry them. And well, of course, those who are familiar with semantic web technologies will say that yes, it's already quite reminiscent. And well, indeed, one could say that RDF satisfies quite a bit. Well, let's now look at how. Well, first of all, as most of you know, RDF is a pretty simple data model. Consists in formulating everything in the form of triples, subject, predicate, object, where object where all the three might be basically a URL, if you like, if you simplify. This tells a bit more, but for our purpose, it doesn't matter. It's a unique ID, you could say, globally unique ID. Or object could be also a literal. So of course, when you have thus it's also a graph, a data model, and of course, when you have a graph, you want some way. Eventually, you want to have terminal nodes which have the data. So that's what the literals are for. Well, among these things, so what RDF satisfy, of course, is standard, and there is open source tooling. It's expressive, and it is quite resilient in the sense that, well, since the data model is so simple, so your schema change may result is just invalidation maybe of some amount of your triples, but you don't have to redo your whole database or do some extensive database maintenance. And another thing is that, since any RDF document is essentially a list of triples, what it means is that it's very easy to concatenate two completely disparate data sources. So no matter which schema they adhere to, no matter what they describe, it's very easy to merge them into one document. So this requirement, the last one, is satisfied naturally by RDF. Then, well, that's about RDF. What about the other piece? What about the OL? Well, for one, OL stands for Web Ontology Language. So it even has the word ontology in it, which of course rings a bell, or is already a symptom or or a sign that it might be something relevant for us. Well, then about the means, well, it has basically everything. Well, it has enough of means for expressing knowledge, classes, subclasses, properties, and ranges, domains. Well, up to this point, actually RDFS, which has this, and then there are cardinality restrictions and much more. We'll actually look, as I said, we'll look at what one can do with OL a little bit later. Then OL is expressed in RDF, quite naturally, and apart from the ontology module, in it also support instances. Then very important thing, which we'll look at next, is the all imports. The mechanism of importing. So one ontology can import another. We'll see why it is useful for us very soon. And of course there is tooling for all as well, which is free. There are two branches of Protege. There is another which are ontology editor, which support all. Then there is top grade composer, another one. These are the most popular ones. And then there are also reasoners. It's it's a software which this will be something we'll look at later actually. Now, how would we match then? Well, if it looks like a good idea, then how would we exactly match our situation, our modeling need in Capish with RDF and all? Well, we can, to begin with, we can look again at the at XML, and remember that we have several layers of abstraction, you could say, here. First is the structure of the object itself. It is pretty much carved in stone, one could say. So these tags, the names of these ones, the structure that the key is sitting inside, and then there are fields, and they may be in a group. So these aspects, they are solid. So so it's this is a basis, so to say. Then this one, in its in its turn, the Capish data model, it gives the structure to the Capish ontology. So the fact that it's a simplified picture, as I said, that the fact that it looks like that is predetermined by this one. So we could say that the Capish ontology structure is sitting here. It's you can think this as a dependency for this. Then, of course, the ontology structure predefines how the ontology itself looks, and in its turn, ontology itself is a schema to the actual Capish objects. So you could say that in this stack you have an abstraction growing downwards. You have the most concrete thing is here, is the actual XML, is the actual data objects which are being emitted from the conversion system. This is the goal. And then you have the metadata to it, which is Capish ontology. And then you have metadata to Capish ontology, it's the structure of it. And then, well, in a way, this one is defined by the Capish object structure, but then, well, you can't really call this a metadata to this, but still, somehow the concreteness grows this way. Now, How would we represent it with all? Well, quite naturally, actually, we might express this one with all directly. We could describe so the knowledge. So essentially, we could describe this with all ontology, pure ontology in the sense that it has only classes and properties. And then the content of the Capish ontology, which is a data to this metadata, would be all instances. So here, then, we also have an arrow, which also goes downwards, but this, in the context of all, it's all imports. So this is a data, this is metadata. Now, there is a blank place here, and it's there for a reason. It's because there is nothing there. There is no counterpart, no all RDF counterpart here for us. This is because we do not emit anything which is related to RDF or all. We emit Capish objects, so this never leaks. And that's why the title of the talk is Semantic Web Undercover, because it stays invisible to the outer world, so to say. We emit, this is what we emit, but this is what we use internally. Yes, but that was about the ontology itself. What about the conversions? How would we go about representing the conversion instructions, conversion information? Well, we can use the same reasoning with dependencies. Well, we still have the Capish ontology schema represented with all classes at the bottom, and then we have the concrete Capish ontology represented with all instances. Now we need, as we said earlier, well, we need to formulate the conversions in terms of our schema, in terms of the ontology. Well, how would we do that? Well, we do that by introducing a schema for conversion instructions and saying that it actually depends on this one. It imports. It does an all import this schema, this set of all classes and properties, imports this set of classes and properties. So this one, of course, stays unaffected by the import. This one gets access. And then we have finally a concrete conversion ontology which sits on top and imports these both. So it has to know the concrete Capish ontology, the schema we need to conform to in the end, and it of course needs to know its own structure. So this is the way to arrange information data layers, so to say, for the conversion system with all. Well, how would we be helped to do that? By the third biggest part of the semantic web stack, by the triple stores, the databases which store RDF naturally. Well, as it turns out, there is a very useful feature which triple stores support, and it is called graphs. Essentially, it means that you could a single triple store could have sub-stores, you could say, which are called graphs. So it's like a subset, essentially. And when you want, you can view the triple store with, well, you can pick your view. You can mix any amount of graphs you like to look at it. It can be only one, or it can be all at once, or it can be some of them. Well, how does one do that? Well, as we know, the language of the triple store, the query language of the triple store, is SPARQL, and here is an example how we would ask a question to, well, shall I show it? Well, to just these two. If these two are the only ones which we're interested. So here we don't care about these ones, we only want to ask questions to this part. Well, SPARQL gives us this possibility by so-called from clause, where one specifies the graph one is interested in explicitly. So here we say, okay, we define some prefix with the dictionary. This is the schema of the Capish Ontology, the bottom one. And then we say, okay, we want to look at the data from the concrete. This is the all instances of the Capish Ontology called clinical. And well, then we formulate a question, so we get some list of object types and the field names associated with them. Well, what do we need to do to ask a question to this one? Well, it becomes a bit bigger. We need to take both the Capish Ontology, the concrete Capish Ontology, and also the conversion ontology, the graph, the RDF graph containing the conversion instructions. Well, then we formulate our question to it as if this was just one single RDF store and there was nothing else. And well, we say, well, we're interested in which study gets converted and which objects are produced there, and then well, we get our list. The overview of information flow between different elements in this whole machinery could be seen like this: that actually, our triple store with our data layer will be sitting here, and it's called ontology server. And then both conversion system and the editor, they talk to it in a read-only mode. But each of them sees only that which belongs to its area of interest, so to say. We can what that means? Well, we can look a bit how is that achieved? How is that achieved? That it's the same database, but we'll look at different pieces of it. Well, the ontology server is designed to use this feature of SPARQL and to mix the RDF graphs, mix them in combinations which are called projects and exposed to the clients, to the outer world. So for example, this bottom level, the most basic Capish Ontology schema, together with the concrete ontology, they form one project, and it is this project that will be accessed by the ontology editor. If that's all you need to do, then you go and access that one. However, if you need to do a conversion, you need to add more graphs. So in addition to the ontology itself, you also need the conversion information, which is then specific to a project or a customer whose data are being converted. And so then, for this purpose, the ontology server is mixing 4 graphs together and presenting them as a one project. And then it's only the top one which becomes which gets write access. The rest one is read-only, which is correct, because when your concern is conversion, you don't want to edit ontology accidentally. So you only want to change this and access this in read-only mode. Or similarly, one could have potentially another project which then reuses the other 3, and the only difference is the concrete conversion instructions. Yes, so that's about so these were all the basic ideas. These were all the key features of the stack that we used, and here is approximately the architecture of the whole system, how it looks, how it has been implemented. Well, we have 3 dedicated application servers. They don't have to be different machines, but these are different server applications. And so there is this ontology server, which is talked to by ontology editor server and the conversion server. And then we have the user machine, where you can edit, from which you can edit the ontology via web or run the conversions. And here we don't use web, here we use .NET infrastructure, and so it's a Windows Communication Foundation, which is the protocol. And then the server itself, of course, the most interesting for us here in the context of this meeting, is built using Sesam triple store, which is a quite well-known, well, you could say a standard even. Many triple store vendors implement the API, and it runs, so for this reason it runs on the JVM, and then we have our own layer on top of that, which does this mixing, which we looked at, does just this packaging, so to say, packaging of graphs. Well, the rest I think are technical details. We don't need to go too deep into that. To show you something concrete, here are some screenshots. So this is how the actual interface of the ontology editor looks like. Well, you can see directly that the SPARQL actually made it all the way to the top to the user, but it's still internal. So it's us who uses it. Interesting part here is that this editor is, well, it does have some business logic which is specific to us, but for the most part it is quite generic, in the sense that, well, it is being driven by the whole ontology, by this bottom level Capish Ontology, which says, well, that sorry, I just want to show. Yes, it is basically this one. So this ontology says that there are such things as Capish fields, suffixes, attributes, object types, object templates, and so on and so on. And then the interface then is driven, you could say, is driven by the whole ontology. So this list of folders which are here, and then the widgets that pop up here, they are created on the fly by looking at the schema, the whole ontology, which is in the background here. This is the conversion system. This is the first. This is how the interface looks like. So you see, it's pretty graphical as we planned. So the conversion steps are defined in a graphical fashion, and all of this, not only the actual steps, but even the graphical layout, which is here, we represent it with RDF. So it's stored on the ontology server in this top-level ontology, which we looked at, in the conversion ontology. And well, the same holds also for this second step, the ontologizing, as we call it. So here is the place where we actually perform the coupling. So this side is the column names of the harmonized table, and these are actually entities from the Capish Ontology. So the conversion system it sees the ontology, and so it formulates, as we said from the beginning, it formulates the conversion, this mapping, in terms of the ontology. And of course, if another person goes to ontology editor and renames this or this, nothing will ever get broken, because simply because the references are, of course, all the referencing is done with the URL, and the literals which represent all these strings you see here, they of course don't affect any coupling. Yes, that was the next one. Well, that was about it, about the Capish part. I could, well, I don't know, we can take questions, or I can show you how the ontologies look in Protégé a little bit, but to be maybe a bit more concrete, to be less abstract. I don't know, how shall we do? Shall we take questions and short discuss if there are any questions, or shall we go on to the next piece and then discuss everything at once? Do we have any questions already? Was it yes?
What stops you from using RDF natively? What is the advantage of having your own data model?
Well, there are some advantages, of course, to Capish data model. Among others, is that RDF triple by itself is it's too little, so to say. So there is an advantage in having a format which is in having a data model which is almost human readable. So RDF triple is the point of it. Well, one of the reasons of why the object, one of the internal names of the object is a colon, is I will not go into the details of that, but the point is that it has all the information together with the context necessary to understand it. So it kind of is the idea is to encapsulate everything, and the original application of it, or maybe it has affected partly, was long-term preservation applications, where you actually want to create a format which you can store or which you can send as a message, and then you would like the message and the format to contain everything which is necessary for understanding. So when you look at this and it says study patient clinical study and then the Dewey code, there is no way you can misinterpret this. And also partly the idea was that it should be consumable by humans too, so that you can open it in a text editor, and then an expert in the field will understand, and even not an expert in the field will understand what it is about. So that's roughly. Well, that's some advantage. And among others is there may be when it comes to using RDF natively, there may be some performance. We have found some performance issues for the applications that we are after right now. So the existing triple stores didn't really give us the level of performance that we need. Otherwise, we might even we could even keep the data model as it is, and then express it in RDF and then index it there. But unfortunately, it's not yet fast enough. Yes, please.
How many programmers are working at your company?
How many are we right now? 6? Maybe 7. No more questions? Yes. We can take the. We could take the other part. Once again. Yes. Well, the other part I was thinking to show is it has pretty little to do with the previous one. It's about all and how one can use it in a fun way to solve a logical puzzle. Well, the puzzle is called zebra puzzle, and it was originally published in a Life International magazine in 1962. Well, the interesting part about it is that, well, there are so many versions of it available that I learned it first pretty long time ago under another name. It was called Einstein's riddle, and it was formulated in slightly other way, but the essence though is the same. And then now when I announced it, I had this one in mind, but then I discovered that there is another version, the originally published one. The rest is like folklore, but it was this, and it happens to have nationalities. Here they have something about Swedes, British, Danish, Norwegian, German, but which would be very relevant in Scandinavia. But I saw that, wow, they have a Ukrainian. I happen to be Ukrainian, so I have to redo it. I actually did it. This one I solved like 5 years ago, and then I decided, well, I do it again. This is another one, and I do it in another way. And yes, it proved to be possible, but somehow, well, it's not easy. And well, you have to really, it's kind of pushing the limits of all a little bit, or rather, you have to guess a right solution. And I have to give a reference. Actually, my solution has been heavily inspired by another one who has done it relatively recently. So the problem is like this. There are 5 houses, 5 people of different nationalities who live in them. Then they have 5 favorite drinks, they have 5 kinds of pets, and the houses are painted in 5 distinct colors. And so there is one-to-one correspondence to each group. So no house is painted no 2 houses are painted in the same color, and so on and so on. And then there are 15 statements which one assumes to be true, and then one has to answer the question, who drinks water, who owns the zebra? And the questions are like this. So there are pretty simple ones. Well, first one kind of is a context. You understand it actually everything I told so far you understand after having read this. So it's like a context. And then there are simple ones, like Englishman lives in the red house, Spaniard owns the dog. But there are pretty complicated ones too, and this will be interesting to look at. The man who smokes Chesterfields lives in the house next to the man with the fox. How about that one? Not easy to express in an ontology, right? Well, but it actually turns out it's possible, and no problem. And not only is possible to express all this formally in all, but it's even possible to solve, to get a solution for free using the reasoners, the tools which I mentioned. But what they do, they get a list of assertions and then see how much they can derive. How much more facts can one calculate? And it turns out one can calculate everything. So from these statements, if one programs them, one can get answer to everything. So who lives in what house, which color, and so on. And of course, it would take too much time to do it from scratch, but I will present you already a solution and then show some bits, show how it's done. Okay. So one usually begins with classes. The top class in all is called all thing, and everything there is a subclass of all thing. Then, well, we have some key concepts. We have drink, house, person, pet, and smoke. We create those. Then we say, and this may be obvious for a human or for a programmer who develops in object-oriented languages, but it's by far not obvious, and it's not taken for granted in all, that these all classes are distinct, that they have no overlap. So one has to specify it explicitly, one has to say that, for example, drink is disjoint with house, person, smoke, pet. Well, when one does that in Protege, one gets corresponding statements about the other counterparts too. So we need to say that. Then the house. Well, how would we? No, let's take a simpler one. Then, what is a drink? Well, we know that there are 5 drinks. Well, how do we define it? Well, it turns out in all you can define individuals. Well, just like that. You open the tab and then you say, well, I define an individual which is called coffee. But you don't need to state anything about it in the beginning. And then you say in your class definition of drink, you say that your class is equivalent to one of these instances. So these are the instances which comprise this class. And then again, something that would be obvious to a human but is not obvious to a computer, you need to be explicit about saying that coffee is not the same as milk, orange juice, tea, and water. You actually need to say it, because there is no in all in RDF you could represent 2 things which are the same with 2 different URLs. It's not impossible. So yes, you need to be this explicit. Then the same simple pattern is used for pet. We have a list of pets, and for smoke, that's the list of cigarette brands. Yes, that's what I forgot to mention. Cigarettes were also in. Yes, now come a bit more complicated things. Now the house. We know that houses, well, first, they are ordered. So if we look at them, yes, how do I find the presentation now? Yes, this. Yes. So houses are ordered. For example, there are things like middle house, yes, a blue house, first house. So they are ordered, but then they are also colored. So how would we represent that? Well, we say we create 2 groups of individuals. We say that house is one of these 5, and also it's one of these 5. And of course, we also say that about each of these, we say that they are distinct and so on. But now, next step. Well, how do we represent the geometry of this situation? Well, we need to explain somehow that the houses, they are actually arranged. And there are notions in the statements, there are notions of like immediately to the right of, or for example next to. So we have the direction, and then we have a vicinity. So how do we describe these 2 notions? Well, as it happens, all has means for that. We go to properties. We look here. Well, yes, there are simple ones. For example, drinks. Well, that one is easy. Well, it says that it has the main person, means it's defined on, well, it means that if somebody drinks, it's a person. And it has a range drink. It means if somebody drinks it, it's a drink. This is a semantics of all. It's not the same thing as to say, actually it's a difference. So it's not correct to say that the drinks is defined on a person. The correct semantics of all says that if somebody drinks, it's a person. If something is being drunk, it's a drink. So this is the inference which one is allowed to make. The same here with person and pet. And by the way, functional and inverse functional means that it's one-to-one relationship. There are no 2 pets belonging to one person, and no 2 persons owning the same pet. These 2, functional and inverse functional, they guarantee this. Now the geometry. Yes, then we have this simple one also lives in house, and then we have accommodate. which is inverse from lives in. So if somebody lives in the house, then this house accommodates this somebody, and this is what an inverse property is. This is the notion, and they are supposed to have domain and range inverted. We can actually see it. Lives in, accommodates. Yes, smokes is really easy also. It's just person, smoke, functional, inverse functional. Now the geometry. This is more fun. So first, well, we have is next to, and it's a relationship between two houses. So it goes from house to house. So if something is next to something, then both somethings are houses. Then it is symmetric. What it means? Symmetric property means that if somebody is next to if some house is next to something, then this other house is also next to the first one. This is what a symmetric property means. Irreflexive means that the house cannot be next to itself. That it's only another house that the house can be next to. Well, it's obvious for a human, but needs to be formalized. And this is the tricky part of solving logic puzzles with this, is that you take for granted things which are completely not obvious for a reasoner. So you really need to think through what else have I missed. Now, the left to right to. They are in a relationship with the property is next to. The relationship is called subproperty. What this relationship implies? It means that if something is left to something, then it's also next to it. And the same here. If something is right to something, then it's also next to it. So it's like a sister, brother, and a sibling. So has sister and has brother is a subproperty of has sibling, because if you have a sister, it means you have a sibling, and if you have a brother, it also means you have a sibling. Same thing here. If one house is right to another one, by right to it means immediately right to. I'm sorry, I should have said. So immediately right to means they are next to each other. And so this is how this bit is encoded. Well, then that's actually almost all there is to it, with the exception that we need to say now that house it actually every house is next to something. Got cramps in my feet. Yes, so every house must be next to some house. This is our topologic situation, you could say. And then you also need to say that the house can be next to max two houses, that they are not grouped together but standing in a line. This is coded here. And right, and that was not it either. Now, final piece. We look at the house 1. We need to make an explicit statement that house 1 is left to house 2, house 2 is left to house 3, and so on. House 4 is left to house 4 is left to house 5, but finally house 5 we don't make any assertion here. Instead we say a negative assertion. We say it's not next to house 1, so that they're not standing in a circle, but they are standing in a line. That was it. Now the geometry is defined. So as you can see, it can be a bit tricky sometimes. Then, yes, as I said, they are distinct with the rest of the houses, and then we have the colored houses, which are also distinct between themselves. This is the general setup. There's so much we have to do before we even started to looking at the rules. Now we'll not go through all the rules, of course, but we'll look at some of them. Well, the Englishman lives in the red house. Well, the first one we have done. Well, this is an easy one. We just go and find Englishman. Here it is. And then we make an explicit assertion that he lives in the red house. That was easy. Well, Spaniard owns a dog is also easy. coffee is drunk in the greenhouse. How do we do that? Yes, well, we do it like this. We define an individual, call it coffee drinking person. And then we say that a coffee drinking person is something who drinks coffee, is someone who drinks coffee. And then he happens also to live in the greenhouse. So we create an auxiliary instance for that. And of course, this instance will then turn to be identical with one of the other persons that we have already defined. A couple of other examples, but just a couple of other examples before we run the reasoner. Well, let's take a complicated one. Well, let's take 11. The man who smokes Chesterfields lives in the house next to the man with the fox. And it turns out this is also quite doable, but we need to create an auxiliary class for that. We say that because we can't create very advanced statements about the instances, so we say that we will create a class, and then we say that here is how we formulate the rule. We say that it lives in something which is next to something which accommodates something which has pet fox. A pretty long statement, but it's logically correct, so we can do it even complicated statements. Well, that's roughly it. Then the person, yes, there's also another interesting thing is that person, yes, person is one of these, and then person must drink some drink, must have some pet, must live in a house, and must smoke some kind of cigarette. This was another thing. Yes, well, that's roughly how it's formulated, and how is it solved now? Well, it's done just like this. Yes, and now we can navigate to our individuals and find answers to all the questions. Look, we happened to hit the answer directly. We happen to hit the coffee drinking person, and we see that it has been derived. So this yellowish background says that these are inferred statements. A coffee drinker happens to live in house 5, smoke parliament, and have a zebra, and it happens also to be same individual as Japanese. So now we have our answer about the zebra. Well, we got lucky. And then what was about water? Who drinks water? Well, we can browse and see. Well, we have actually found out everything about Englishman too. Happens to be milk drinking person and old gold smoker, and has snails as pets and lives in house 3. And then the water, then, well, it's a Norwegian who lives in yellow house, smokes coals, and drinks water, and has pet fox. That's it. We solved it. It is claimed that only 2% of people who can solve this puzzle, but I don't know if it's true or not. It's like a folklore which exists about it. Yes, that was all I had for you. Thank you for your attention.